Thank you. Look about right. So let's pick up where we left off, right? So we kind of ran down the elements in biology, and the real kicker of this one, right, is even though we have like 90 some odd naturally occurring elements, over 96% of living things, not just us, everything living is composed of CHON, C-H-O-N. That's the majority of it. Now, the one thing I did want to make sure I kind of followed up on this one, just a little bit, just to kind of complete the thought. There was one thing I always like to really point out, is that even though the lion's share of the atoms in your body are right up here in these four, it doesn't mean the rest of them are insignificant, right? So the important thing to always remember in biology and physiology, the Texas rule doesn't apply, right? Bigger the better. Actually, the bigger it is, the more costly it is, which means the worse it is. So if anything, biology is more like fine cooking, right? Where oftentimes just a little bit of a spice makes or breaks the dish. If you put too much of it in there, you're screwed, right? I mean, unless you want to eat an entire clove of garlic, like an apple, which is good. I'm saying that's a thing, right? But usually if there's other flavors in the dish, from a culinary perspective, the garlic overwhelms it. So a little bit will do you good. Unless you love garlic, like you go to the garlic knot or something like that, and you just basically get over garlicked, which personally I love garlic. So to me, that idea is actually, I've always had delusions of like, one of these days, I'm just gonna take that thing, I'm just gonna be like,
Roast it first.
it'll knock me on my can. That's what I want to do. That or an onion. That's another one, like a nice onion, just like
I can do that.
yeah, that's granted, I wouldn't be able to go out into public for at least a month.
Wear a mask all the time.
As I sort of sweat it all out. That lovely, right? That'd be wonderful to live with, wouldn't I? It's like, okay, you go sleep with the dogs. Because right now they smell better than you do. So that's my problem, not yours. But the other things are important, right? Because they actually play some very important roles. And so just like from a culinary perspective, a fine spice can make or break a dish. The same thing is also true. These so-called trace elements are not to be scoffed at or diminished because they are low in proportion relative to all the rest of the atoms. Here's a good example, the lowly sodium, right? Relatively speaking, there's not a lot of sodium in your body relative to carbon, hydrogen, oxygen, nitrogen, or some of the others. But I can guarantee you that if you didn't have sodium right now, you'd be dead. Why? Because sodium is a required ion for all of your nervous impulses. So everything you're doing right now in terms of your brain actually forming thoughts and decisions requires sodium in order to do it. So if you didn't have sodium, you would basically be dead. Okay. Calcium's another one. If you don't have calcium, you wouldn't be able to actually contract your muscles. And you're thinking, oh, that's fine. I just basically lay there like a vegetable. No, you wouldn't, because you need calcium for your heart to contract as well, which means you wouldn't have a heartbeat, which means you'd be dead. Right? So even though there are not a lot of them, the roles that they play in physiology are titanic. Okay. So that's kind of the important thing. That's the one I wanted to make sure, because a lot of times, we kind of get in that Texas mentality. It's like, oh, well, 96%, that means we can do away with the rest of it. I mean, that's pretty good, right? 96%, most, you would take that as a score on your exam, yes? Yes. Right? But not here. Because that other, 3.7% is basically life or death, basically. So that's the high stakes of biology, right? It's not for the timid. Okay, so let's take a look at chemical bonds. Now that we have some basic ideas about the personality of atoms, right? We talked a little bit about the psychosis of atoms that's set up by the octet rule, right? The tyranny of the octet rule. We know that everybody is crazy except for group 8 in varying degrees of craziness. But now we basically sat down that the only way that as an atom, when you're crazy, that you can maintain perfection or achieve perfection is if you form bonds with others, right? That is basically say associations or relationships where you can cover for each other's imperfections, right? So in tandem, you will achieve perfection, whereas alone you will not be perfect. Okay. So the question is then, what kinds of chemical bonds or relationships between these two atoms that are trying to cover each other's octet rule for each other? What kinds of these relationships do we have? That's chemical bonds in a nutshell. Okay. So basically, we have a couple of atoms that will be forming an association, and what they will be doing is sharing electrons. And so just to kind of show you a little bit about what this looks like, we've already talked a little bit about sodium and chlorine, so that's kind of a good starting point. So it is a perfect example, right? Because we talked about this one. We already know how crazy chlorine is. We already know how crazy sodium is. We've already talked about the idea that sodium wants to desperately get rid of that one electron, and so it does. As a matter of fact, it finds a perfect donor in the sense of chlorine, right? Because this is eager to get that electron, and so it accepts it. Which basically means then that chlorine in its happy place will be existing as a chloride ion, right? Because it's acquired that one electron, filled up that outermost shell, and by doing that, it's achieved its octet rule. It is essentially achieved atomic perfection. So it's happy. Same thing for sodium. If it gets rid of that electron, it falls back on its next shell down, so the full one. And so it will be happy, quite happy actually, as a sodium ion. Now notice, at this particular point, even though technically speaking, you're kind of on your own and you sort of like, have your own identity now, you're still in association with each other, aren't you? Technically speaking, you got kind of like a little bit of a custody agreement over that electron. And it's only within the context of the custody agreement are you happy that there is a bond. Okay. Now, what we just basically made here obviously is salts, right? Sodium chloride. And any salt is like this. So basically, when you take a look at a salt, in this particular case, you'll notice you've got positive ions, sodium, right, that are the purple ones, and negative ions, which are the chlorides. And because they're positive and negatively charged, they can stack in a crystalline form in a very orderly form. And that's kind of what you're seeing here. So you see that the negative charges are stacking in such a way that they are surrounded by the positive charges, right? So you kind of keep the one you're attracted to around you. And the same thing is also true for the positives. So the positives will stack the negatives around it. And so you kind of have this very orderly kind of stacking, right? Positive, negative, positive, negative, positive, negative. And it makes it a very orderly type of a crystal. And that's what basically a salt crystal is. Okay, it's just got a stack of these ions. Now, let's take a look. And what I want to do is I want to do one of my famous insertions because I want to put everything together. There's a couple of ideas that we have kind of spread out over here, about a half dozen different slides that I want to pull together. But before we do that, what I want to do is I want to sort of zip forward a little bit. To this one here. So this one I want to cover first before we start talking about bonds, because a lot of how you characterize a bond has a lot to do with this particular trait, electronegativity. And so let me, I'm going to go ahead and insert my slide. I'll insert it here. Yes, insert. Did you insert anything? What did I do? Oh, new slide. Sorry. Would help to actually tell it to drop a new slide in. It's like, what do you want to insert? It's only Wednesday. I'm already feeling the wear and tear of a Friday. Which basically means you have a lot to look forward to on Friday. Be like, whoa, this dude needs help. But so why electronegativity? Because this electronegativity is a physical property that you run across in atoms, and there's several physical properties that you study in chemistry, many of them, and usually they show what's called periodicity. That is to say that their behavior you can predict from the periodic table. They overlay perfectly on the periodic table. Electronegativity is one of them, and there's others. But in electronegativity, it's very simple. This is basically something that's intrinsic as a physical property to each atom, and each atom is slightly different. But Basically what electronegativity is the affinity that an atom has for electrons. Okay, so you can think of the electronegativity as sort of electron suckiness. That's a technical term. That's a
Suction.
yeah, like a vacuum cleaner, right? Basically, you suck it toward you. Sometimes I say magnetism, but magnetism is actually a real thing that's different, right? So suckiness, that's my technical term. Yeah, so how strongly can you suck electrons towards you, right? Exactly, like a suction, right? And so some atoms have a strong suck on electrons and some not so much, okay? So how do you know which one's which? Well, it's very easy because the periodicity of electronegativity is such that when you take a look at the periodic table, and this is important, that's my periodic table, it increases going up the periodic table and to the right. So who has the greatest electronegativity? Well, the nobles don't count. It would be fluorine, right? And the nobles are noble because they've already achieved perfection, so they just sort of check out of everything. They just, I already know the answers, I'm out, right? So that's kind of the way they are. So yeah, fluorine has the highest. Who has the lowest? Francium, right, has the lowest because it's both to the left and down. And then, of course, now you can see everything in between has varying amounts of electronegativity. The reason why this is important is because when you start talking about bonds, electronegativity is what characterizes how they behave in a bond. So let's go to, where is it? There it is. Yes, it's basically how they set themselves up, right? Because each bond is characterized ultimately by this intrinsic physical property of atoms. So let's take a look at it. So what I want to do is I want to basically line up the bonds. And there's 3 of them. Let's start off where we began. That's with what's called the ionic bond. The ionic bond is essentially where 2 atoms, usually a metal and a non-metal, differ drastically in electronegativity, and they transfer electrons. We talked about one already, right? Basically, what's a metal? Obviously, you've got transition metals. We're not talking about those. Most of what we're talking about is these 2 guys over here, group 1 and 2, right? So the alkali metals, alkaline earth metals. These guys are metals. Who are the non-metals? These guys over here, right? So group 6, group 7, those are the non-metals. The red ones are gases, the blue ones are liquids. But for the most part, there's just like a little zigzag line that goes between aluminum, gallium, and it kind of zigzags down between tin and bismuth and polonium that forms the divider between the non-metals and the metals. So they're kind of transition metals on this side of the zigzag, and they're sort of non-metals on that side. So basically, those are the non-metals, and these guys are the metals. So basically what you have is a non-metal or a metal with a non-metal. Notice sodium, a metal with a non-metal, gas, chlorine, right? Potassium, bromine, bromide, potassium, bromine, right? So these are metals with non-metals. In those cases, the electronegativities are so drastic, very low, because way over here to the left, very high, way over to the right, that you basically get a disparity or a lopsidedness in the suckiness of the electrons, right? In this case, for instance, bromine, very electronegative. It's going to be sucking the electrons in question way over toward itself. Not so much for potassium or sodium, okay? And so that disparity basically, because it's so lopsided, basically creates a situation where it's like literally a transfer of the electron. Now, what happens if you're a little closer in electronegativity? That's where you get to your covalent bonds. So this is basically where two atoms share electrons. And there's two different types. There's polar covalent, where there's unequal sharing due to unequal electronegativity. And then there is nonpolar covalent. This is equal sharing due to equal electronegativities. So let's take a look at this here. So we have our nonpolars and our polars, but usually this is the example. So these guys right here are going to be an example of nonpolar covalent. Take a look at this one, hydrogen. How many valence electrons on hydrogen? 1. How many electrons does it need to become perfect? 2. So it just needs one bonding partner, yes? So as it turns out, hydrogen says, hey, guess what? I've got one, my fellow hydrogen has one. This is easy. Why don't we just share and become what? Bonded together. So that's basically what this is. So this represents a pair of shared electrons. And this is basically what they're doing. So this basically, the shared electrons, is the covalent bond between the two of them. What's the electronegativity? So is the electronegativity of this one greater, less than, or equal to the other one? Because they're the same thing, right? Electronegativities are equal. Therefore, nobody has a greater suck on the electrons than the other. So it's a stalemate, right? If you take a look at oxygen, let's take a look at this one, right? Electronegativity, is it greater, less than, or equal? It's the same thing, right? Oxygen, so it's a stalemate. But let's take a look at oxygen. How many valence electrons are in oxygen? 6, right? So, oops. There. Right, so you got 6. There's one here, there's one there. Guess what? The other oxygen, same thing. 1, 2, 3, 4, 5, and 6. So what does oxygen do? Hey, I need to share something. So let's go ahead and do that. Okay, let's share. There's one. It's kind of a little weird, but there's one share pair. And it's like, you know, I got another one. So let's go ahead and share these two right here. So I can form 2 of them together. And that's kind of what it looks like. So you have one shared pair here, one shared pair there. That creates what's called a double bond. A little bit stronger. Oxygen can do that. There's only one, however, that can form a triple bond, and that's nitrogen. In this case, it's the same basic diff, right? So here you have how many? 2, 3, 4, 5. So you have 3, right? 1, 2, 3, 4, 5. So you basically share 1, 2, 3. From what I understand, I mean, the only one this is the only one that does that. So nitrogen can form triple bonds with other things like carbon, rarely, but nitrogen is always involved usually. So that's the thing. But these are all what? Non-polar covalent. Why? Because the electronegativities are equal. So this would be an example of a non-polar covalent. So in this case, the electronegativities are equal. In this case, the electronegativity of 1, A, whatever that is greater than the electronegativity of B. And in this one, the electronegativity of atom A is very, very much greater than the electronegativity of B. The reason why I like to use this in view of electronegativity is because you can see the different bonds, ionics versus the 2 covalents, as just different points on this continuous spectrum of how strongly polarized is your suck, right? Your electron suckiness. If it's extremely polarized, then you get so lopsided that it becomes a transfer. If it's not polarized at all, then you get the other extreme, which is basically equal sharing. So when I actually said that this is very similar to like a custody battle, this very much is that way. You can actually see this as a custody, right? Because when you take a look at a custody agreement, it takes on different perspectives, right? Different flavors, depending on the nature of the two people involved, right? The two parents that is involved, right? So let's take a look at what this would look like socially. Get ready for your sociology, biology. Let's take a look at the ionic one. The ionic one is basically the one night stand, right? This is the situation where it was just a one night thing. The kid happened and, you know, you kept it, assuming obviously you kept it, right? You're not going to annihilate electrons. Right. So you kept the kid and now there's this issue. Yes. You know, the deadbeat is basically like, you know what? Do whatever you want. Keep the kid however you want. But as far as you're concerned, I don't exist. This never happened. I'm not a dad. I'm just going to go on and do my thing. Right. Who's the deadbeat dad here? Sodium. Yeah. Right. It's like, here, take the kid. I don't exist. I'm not a father. It didn't happen. Right. I'm out. And then of course, oftentimes on the other side of it, the mother's like, well, no, I really want a kid. I'm going to keep the kid. I don't care what you say. This is mine. So actually, you're kind of a creep. I sort of regret every moment of that night. So if you just basically spontaneously combusted, that would actually be the best thing for all humanity. Is that real? Yeah, that's real. That's how it goes down. Right. So in that case, what you have a very strong, dominant possession. Like, listen, this is my kid. I've waited a long time for this kid. I'm not going to squander it. Right. So this is mine. Get out, get away. Right. And so that's like an extreme lopsided. You wouldn't really call that a custody situation, but technically speaking, since you actually both have chromosomes running around on the planet, it is a custody thing. Sorry, biology says you are custody. Whether you admit it or not is psychology, right? The fact that it is biology. So just don't run for president, because then all of your one night stands will come out of the woodwork wanting money. That's a little cynicism there, but yeah. So yeah, it always kind of makes me chuckle every time you run across a flawed individual running for office and all these skeletons in their closet. I'm like, it just kind of laughs. It's like, yeah, that's why most of us aren't dumb enough to run for president, because we all have skeletons that we'd rather keep in the ground instead of just walking around on the planet. But anyway, that's neither here nor there. Okay, so that's obviously an extreme, isn't it? Okay, now let's actually pretend like these two people actually loved each other at one point. You know, they loved each other enough to have a kid. They were in a relationship. It didn't work out for one reason or another. And generally speaking, when that happens, there's a parting of ways. But usually you kind of come down to variations of some sort of a custody agreement. And it goes something like this. Generally speaking, what we see most of is something that kind of reflects more of like a polar situation, right? Generally speaking, there is a dominant parent. Often the mother, but not always, right? Fathers are getting more dominant work these days. But there's usually a dominant parent, and then there's usually some sort of an agreement, right? So that's fine. If you want to visit on holidays and birthdays, that's great. That's a little polarized, right? So, or you could be like, you can do every weekend if you want, that would be fine. You can visit the kid every weekend or whatever. So that one's a little bit much, so they're a little more closer together. So you don't have as much polarization between who's dominant and who's checked in, who's checked out, kind of a thing. And so you can imagine that there's a whole range of possibilities in there that you could potentially get. And this exactly reflects just the way the atoms are, right? Because you can have a whole range of how close these electronegativities are, which gives you varying amounts of sharing between these individual atoms, and that can have a lot of shades to it. Then there's the rare one, but you do see this from time to time, where the two partners are, they kind of, it was maybe an amicable separation, or at least it wasn't so catastrophic that they weren't able to come back together at some point and say, listen, we're not a thing, but I think we're better friends than we are spouses, right? But we have this kid that we both are in agreement on pretty much, and we can work together well as a team, as equal partners, right? So there you have kind of like this sort of dual sharing of responsibilities where both parents are actively involved in the life of the child, right? I mean, now that's obviously a lot rarer usually, but you do see that from time to time where there's two very energetic and active parents involved in it. That would be an example of a non-polar covalent where you have pretty much duality, equality between the two dominant parents who agree to equally share this custody of this child, right? So that's just basically two atoms with similar electronegativities agreeing to share equally the electrons that they're sharing between them. Okay. And so that's basically how you look at it. And that's exactly the way the atoms work, right? They basically sort of come to their custody agreement depending on their electronegativities. Okay. Now, I gave you some examples of ionic because we looked at salt, right? I gave you some examples of non-polar covalent, but I haven't given you anything about polar covalent. Why? Because there is one polar covalent molecule that's the best one in the world. What is it? Yeah. So it's an oxygen, which has how many valence electrons? Valence electrons? What group is it in? I heard it. Nope. Nope. Keep guessing. Yes, it's in group 6. It's got 6 valence electrons, right? So what does that mean? How many does it need in order to? So what it does is it says, hey, I'm just gonna scrounge around the universe here and I ran into hydrogen. Who has one? Who needs one? I have 2. I need 1. So you know what, hydrogen, I'm not gonna worry about this one, but why don't we share right there? Oh, hey, wait a minute. There's other hydrogens around here. You got friends? Give me a call. Form another one. What did I just make? Water, right? So this is an example of a polar molecule. Why? The electronegativity of oxygen is greater, equal, or less than hydrogen. Greater, right? Because all the way to the right, hydrogen is all the way to the left. So what does that mean? That means all the electrons in the cloud get sucked over to oxygen. So what this looks like when you take a look at the cloud is you kind of see this big poofy electron cloud sort of coming all the way over to oxygen. What that means is the electrons tend to spend a little bit more time over here on the electronegative atom than on the others. This kind of creates sort of a quasi-negative pull to water. And then by absence, because the electrons are getting sucked to oxygen, the hydrogens tend to be slightly positive. So this is what's called a polar molecule. Because it has a positive and a negative pole, right? A positive end and a negative end. However, within this molecule is a bond between oxygen, right, and hydrogen, which is polar covalent. Because the electrons would go that direction, right? Because oxygen has a greater suck on the electrons. Now, here's the question. And this is always one that there's 2 different discussions that are going on here. From a chemistry level, we talk about bonds themselves as being polar and non-polar. But then there's a separate discussion where you talk about the molecule as being polar or non-polar. Oftentimes we'll talk about the molecule, especially as we start to get more deeper into macromolecules. And here's an example. So what I did here with water, it's an easy one. It's both a polar molecule because it's got a positive and a negative side, right? But it's also got polar bonds inside of it, right? However, we can split those two. And I want to kind of throw you a curveball. I want you to take a look at this one here. Anybody know what that is? That's methane. Of like cow fart fame, right? That's their human fart fame. Fart fame. Just if you're a fart person and that just hits you in the right spot, then this is your thing, right? So enjoy. But if you take a look at the carbon hydrogen bond individually, is it polar, non-polar, or ionic? Polar, why? Correct, right? Because it's further to the right than hydrogen. So here we have a polar bond, right? But is the molecule polar? That is to say, does it have a negative and a positive end? You would be right. But why would you be right? Yeah, right? It's non-polar molecule because the charge is evenly distributed. Right? So all these electrons are going kind of like all in the same direction. You don't have a negative side and a positive side. So you can't define, oh, this is the negative end of it, this is the positive end of it, because it's symmetrical. So if you can't get that lopsidedness in charge, it basically means it's a non-polar molecule that is composed of polar covalent bonds. That makes sense? A little tricky. Not only is water soluble, but actually water defines solubility. It transcends solubility. So water is not soluble. Things are insoluble in water. So, and we'll talk about that. That's one of the properties of water we'll talk about. Exactly. Water is the solubility. Okay. So those are your bonds. Ionic, the covalents, polar and non-polar covalent, right? So what's up, and this is a little bit of a topic shift, although the book doesn't, the PowerPoints, not the book, because there's whatever. Right. So the PowerPoints don't do a good enough shift here to frame this well enough for students, because oftentimes it's confused because you just come off of talking about polar covalent and non-polar covalent bonds, and now we jump into hydrogen bonds. And it makes a lot of sense, right? Because now all of a sudden you're thinking, oh, well, this is a chemical bond. No, it's not. Right? It's a misnomer. It's not actually a bond. Not the way we've been talking about. It's not a bond between two atoms that are sharing electrons to satisfy their octet rule. None of that is true of a hydrogen bond. What this is actually more appropriately defined as, and the next slide as well, as intermolecular forces of attraction. You're not talking about forming relationships between atoms to satisfy your octet rule now. You're talking about you're going up the next level up. You're going to the molecule level, and now you're talking about the interactions that occurs between molecules that are polar or non-polar. That's the reason why I had to parse the difference between the polarity or the non-polarity of a covalent bond versus the polarity or the non-polarity of a molecule. Okay. Because now we're going to start talking about molecules. So exactly what is a hydrogen bond? So a hydrogen bond is basically, this is just too much stuff here. Basically a hydrogen bond is, by definition, an electrostatic attraction between the positive hydrogen of one molecule and the negative of an oxygen, nitrogen, or fluorine of another molecule. Generally speaking, this is your chemistry term. Generally speaking, you don't see fluorine in biology, only in chemistry. There was no fluorine in you at all. So that's not a thing, but there's a lot of oxygen and nitrogen in you, right? CHON, that's part of your CHON. So the positive kind of pole of one will be attracted to the negative pole of another, just like a north and a south pole of a magnet, okay? And this is basically an electrostatic attraction, not unlike the exact same set of physics that you see when you rub a balloon on your head and you let it go. What's going to happen? Yeah, it stays there, right? Why? Because what you did was you were rubbing electrons off of your hair. It was accumulating on the balloon. So you're getting a charge disparity. You look a little more positive. The balloon looks a little more negative. Positive and negative attract. So electrostatically, they're attracted to each other. So when you let go, the balloon sticks to your head. Okay, that's the exact same set of physics of a hydrogen bond. And so ultimately then, when you take a look at a hydrogen bond, these intermolecular forces of attraction are not strong. They're not like a covalent bond, right? To break a covalent bond, you have got to really add some energy in there. I mean, it is ugly brute force to break a chemical bond. But intermolecular forces of attraction are weak, right? Just like the attraction of the balloon to your head. Is the balloon now part of your body? No. Is it fairly easy to pull the balloon off? Yes, that's because it is a weak interaction. So these are weak interactions, and individually they're weak. They're very, very weak. But in a cumulative, they are actually quite strong. Nope, that's next. Right. So this basically represents how polar molecules attract to each other, right? Because why? Because you have to have a positive end and the other molecule has to have a negative end. That means you have to be polar, both of you, in order to have an electrostatic attraction to each other. So this explains the reason why your two polar molecules are attracted to each other and why they stick to each other, is because of that electrostatic attraction between each other, associated with these partial positives on hydrogen and these partial negatives on oxygen and nitrogen. However, it doesn't really explain the reason why nonpolar molecules are attracted to each other. Think about it. Nonpolar molecules do not have a positive end, do they? They don't have a negative end either, do they? So how do they stick together? How does oil stick to itself? That's the next one. So the van der Waals attractions are even weaker than hydrogen bonds. But what you have in a van der Waals reaction or interaction is something that we learned about in chemistry. And it goes something like this. So generally speaking, when you have a polar molecule, and I just want to schematically draw this out, right? So when you're a polar molecule, you essentially are characterized by a negative end and a positive end. And if you're polar, that's permanent. In chemistry, we have a term for that. We call that a permanent dipole. Di, two poles, positive and negative, right? But you're permanent. That's the way you are. Water, for instance, is a permanent dipole. It always has a negative end on the oxygen. It always has a positive end on the hydrogens. That's a permanent dipole. And that's how we understand these interactions, because the negative end of one molecule attracts the positive end of another, and that's how they stick together. Okay. So the question is, how do van der Waals attractions? Well, van der Waals attractions actually form what's called a temporary dipole. So these guys will basically form a temporary dipole. Okay, let's explain how these work. So in this particular case, we have areas in the molecule where it's like an oil or it's like a lipid or something. It's nonpolar. That create patches. I'm going to lay some words on you. SAT words. Ephemeral, flickering clusters of charge. Called temporary dipoles. What does that mean? Let's take a look at it. In any given molecule, let's take two nonpolar molecules. Remember, the electrons are whizzing around their clouds, yes? Every now and then, just by happenstance, just by random luck, you'll get the lopsided washing machine effect, where for a brief moment in time, all the electrons will converge on the same spot just by random chance. And when they do, for that split second, ephemeral, right, which means fleeting, there is like a little patch that's very negative. And that creates your temporary dipole. So it almost very, very fleeting. It creates this little negative-ish patch. Well, where the electrons are not, right? So if they're all right there, then where they've deserted from is going to have a slight positive-ish flavor to it. So you're going to kind of create this sort of like temporary patches of charge called the temporary dipole that's just there for just a second, right? Because as soon as all those electrons converge to the same spot, creating that little negative patch, they all scatter and go somewhere else. And then just by random chance, they'll come together again somewhere else, creating another little negative patch, and then they'll disperse. And they'll come together again just by random luck, and then they'll kind of create another negative patch and they'll disperse. And so you have these like little flickering clusters of charge. Like you'll have a little negative patch in there and then it'll disappear. And then you'll have a little negative patch over here and then it'll disappear. And then it'll come up over here and then it'll disappear. Okay. That's that flickering clusters of charge idea that's ephemeral that we call a temporary dipole. As it turns out, the molecule next to it is doing the exact same thing. And as they do this, then the little flickering positive cluster on one molecule will be gently attracted to the negative patch on the other molecule for just a brief moment in time before it gets dispersed, and then it'll kind of let loose. So it's kind of like it'll just sort of suck toward each other just a little bit, and then they'll let go, and then just a little bit and they'll let go, and then just a little bit more and they'll let go as these charges sort of come together and then disappear and then come together and disappear. And that's enough to hold these nonpolar molecules together so that when you pour oil out of a bottle, it pours in a column because those molecules are stuck to each other. It doesn't just fly apart. So that's van der Waals attractions that's doing that. But it's really, really weak and very easy to overcome, okay, which is a good thing. And that's intentional, right? Because where covalent bonds and ionic bonds are intended to be permanent to create stability and kind of static framework of a molecule, the intermolecular forces of attraction are designed to be dynamic, to give you a lot of flexibility so that you can kind of move about the pocket, so to speak, if you want to use quarterback terms, right? So those, by the way, have a lot to do with one of our next major topics that's coming up here, which is the properties of water, which we'll get to here in just a second. But that's formed on these intermolecular forces of attraction of water. So we'll take a look more deeply actually at the consequences of hydrogen bonds as we move forward. But first of all, I want to take a little brief interlude in the chapter to kind of sketch out, because we'd be negligent in our duties if we did not, the idea of chemical reactions, right? We already talked a little bit about these, but basically when you take a look at your chemical reaction, always remember that in a chemical reaction, what you're doing is you're forming chemical bonds. Why? To achieve your octet, right? That's why you come together. Typically in any given chemical reaction, that's exactly what's happening. So it is a reaction between two players who are coming together for the exact same purpose as any other chemical reaction, by the way, which is to satisfy your octet. right? To get yourself perfect. So typically speaking, the unhappy partners oftentimes on the left-hand side of the equation are the reactants. So these are the things that are coming together to form various associations. Then of course you have the reaction progress, and then ideally is you form your products. Now, a couple of things to notice about your basic chemical reaction. Number one is, and this is where we want to start, is a principle in chemistry that we call the law of conservation of mass. How many of you guys have heard about that one? So this is basically it's a chemistry law, and basically what it means is that no mass is lost or created in a chemical reaction. Okay, that's nice. Well, what does that mean? So what that means then is that the number of atoms you have on one side has got to equal the number of atoms that you have on the opposite side. So how many carbons do you have in your reactants? 6, right? So 6 carbons, we're good. How many carbons do you have in your products? 6. Has to be, right? You can't lose carbons, you can't gain carbons. How many hydrogens do you have? 6 times 2, 12, right? How many in your products? 12. How many oxygens do you have? So you have 6 times 2, which is 12, plus 6 more, which is 18, right? And how many do you have in your products? Did we lose anything? Did we gain anything? No. So what does that basically mean? What that basically means is, what are you doing then in the chemical reaction? Well, all you're doing, yeah, you're just changing seats. So what you're doing is you're taking 2 reactants that, by the way, are bonded to each other, satisfying each other's octet rule. You're breaking bonds that exist. So that means you're throwing atoms into a state of disrepair now. And you're basically assigning them to new bonding partners in favorable combinations that give you something different. So all you're doing is taking existing bonds, breaking them, and creating new bonds between the exact same atoms. Okay. So you're just mixing up the way they're all connected together. And that's always true. Okay. So what are some things that affect our chemical reactions? So how can you speed them up, basically? Well, a couple things. First of all, you heat it up, you're going to speed it up, right? So this basically speeds up the reaction. What's another way we can affect it? Well, we can add reactants to push it forward. We can add products to push it backwards, right? So either putting more reactant or more product in there will affect the rate of the reaction. And the other one is a catalyst. A catalyst is basically a molecule that has 2 traits to it. Number one is it will speed up a reaction. And number 2 is it will not be consumed by the reaction. And these 2 have to be true if it's going to be a catalyst. Correct. The reactants are transformed by the reaction. The catalysts are not. You literally can put a catalyst into a reaction and it'll come out completely the same as you put it in. Okay. It's not a participant in the reaction itself. It's just a chaperone, if you will, right? Or facilitates the activity. Now, the important thing also when you're taking a look at chemical reactions in biology that we're also interested in, this is like the biggest actually point of this one. The rest of this is just chemistry 101, but this one is actually biology, biochem, which kind of feeds our biology, is this one here. This cannot be overstated. In biology, what sets us apart a lot of times in the way we think versus chemistry is in chemistry, you're oftentimes looking for reactions to go to completion, right? So you want to calculate percent yield. So you want your reaction to basically give you 100% yield. So you want it to go totally to completion, right? The idea is it doesn't go to completion, that represents some inefficiency in the reaction and things of that nature, right? So you're always looking at completing the reaction. You don't really get to equilibrium, these reversible reactions, until Chem 2. But in biology, we're not interested in reactions going to completion. We actually want the reactions to have both forward and backward. So for instance, if we have A plus B, which goes and gives us C plus D, it has a forward reaction and a reverse reaction. That is to say that C plus D can fall apart into A plus B. Now, how do you know which one you get? Well, circumstances will determine this. In some scenarios, you need more C and D, so the forward reaction is favored. In other scenarios, you need more A and B, so the reverse reaction is favored. Depending on your circumstances, by the way, if you've looked outside, circumstances change a lot, right? Your environment is constantly in flux. Why? So that's the reason why you need reversibility. You need the ability to sort of bob to the right, bob to the left as the environment is throwing punches at you, right? If all you did was just stand like a statue and just go to the right, guess what? The right hook's coming for you, right? You have to be able to break right and then go hard left again to be able to avoid that right hook as it's coming at you. If you can't do that reversibility, you're screwed. Okay, so reversibility in chemical reactions is a critical component of all biology. And it's because we need that flexibility to match up to our ever-changing environment. Okay. Okay, let's take a look at water. So water is the elixir of life. It's what we're made out of. It's most of what we are, actually. Your blood plasma is like 92% water. So this is basically it. This is the reason why when we're out there on other planets, what are we looking for? Not just any water. We're looking for liquid, ideally, right? And there's a reason for that. And we'll talk about that here in just a second. But basically, when you take a look at the structure of water, we already took a look at it, right? So basically, this is a structure where you have these electronegative oxygens paired up with these not so electronegative hydrogens. And this is going to give you your polar water molecule, right? And this, by the way, ignore this. Oxygen is not partially negative. It's partially, or not partially positive, partially negative. This one should be positive. So that's just a typo right there, right? So this is basically your water molecule, right? So where you have your oxygen and connected to your two hydrogens, which are slightly positive. And the nice thing about this, we kind of sketched this out. So you can see the Bohr model, right? So we wrote up the Bohr model where you have basically, you got your two first shell electrons, and then you have your outer 6, right? And then of course, 2 of these guys, these lone pairs, are happy because they're already paired up in their orbitals. And then the other 2 have to be shared between the hydrogens that you share and the oxygen. So that's your bond, right? And then everybody's happy, right? Because everybody's full, hydrogen's full, oxygen's full, everybody's happy. And so when you kind of do this and you kind of imagine that when you form these bonds, you're kind of changing the shape of the cloud a little bit. You're changing the shape of the way the molecule looks because of now the addition of these extra atoms. So now you've got this extra component to your molecule. And it's not just about you and all those little orbits, those little orbital peanut shells and things like that. It's not just that, it's you and somebody else now. And the interaction between you and your hydrogens is going to change a little bit about the way the cloud itself is shaped in nature. And so what that does is when you have this particular format, it creates a very common structure that we see in water. Notice the way I draw water, I draw it as a bent molecule. A lot of times students will ask me, well, how come you don't just draw it like straight? Just H2O. And the reason is because it's not straight. And of course, then the question is, well, how come? Well, this is how come. Because when you take a look at any kind of a molecule that has 4 clear like orbitals, 4 positions for bonding, it basically forms a traditional structure of those 4. Carbon does the same thing, by the way. And it's what's called trigonal pyramidal. And so what happens is the bottom 3 bonding partners form what's like a sort of a pyramid shaped shape to it. And if we use carbon, I'm going to use methane as an example here, right? Carbon is like in the middle of that. So you have the 3 bonding partners pointing down, and then there's like a little stick that's sticking above carbon that kind of creates that, that third component of it. So it looks something like that shape-wise in terms of the actual shape of the molecule itself.
So that's what makes methane polar.
Non-polar, because it's,
Non-polar covalent.
yeah, because it's all equally distributed and it's well balanced and symmetrical. So all the electron cloud doesn't ever get lopsided. That's the reason why. Now, when you take a look at this, typically what you'll have is you'll have a hydrogen here and then 3 hydrogens down here, and that's your typical shape, right? So kind of a tetrahedron that you have here. But now when you take a look at water, you don't have 4 bonding partners, do you? So you don't have that full tetrahedral shape. So what you do is you eliminate one of those because you've got a lone pair there, right? So that's going to be held in close to the oxygen because it's electronegative. You have another lone pair there, so you're going to take out another one of those options, right? So this is kind of like if you're oxygen, let's convert this to oxygen, right? So you're gonna, this one's going to be a lone pair. This one's going to be a lone pair. And what do you have left? The other 2, which is bent. Why? Because that's what a pyramidal shape looks like. If you take away that one edge, then what you got is a bent molecule, which is the reason why water is bent. The reason why we mention this is because, especially when we get to proteins, shape and the shape of a molecule that starts now at this level is everything. Okay, so there's a lot of shape fitting when it comes to especially protein and the way proteins work. Yeah.
So when it comes to water, bad light, the negativity on that side, that water tries to go from the molecules together.
Like salt or something like that, or other polar molecules.
Over water molecules.
Yeah, I'm going to actually draw the structure of water here in just a second. And partly because it starts to form now what we have as the properties of water. And here I go again. Love me some slides. No. Yes. So one thing to understand is that what we're going to list here now is a list of all the properties of water, not just like, oh, gee whiz, isn't that cute, but why they're critical to basically underscore and to develop a foundation upon which biology needs. So it's going to give us the things that we need to be a functional biological organism, right? So we're going to see its biological application. By the way, the properties of water all come to us by one very simple thing: the hydrogen bonds of water. Okay, so the H bonds, we'll get back into that a little bit. We'll kind of sketch that out a little bit. But what I want to first of all start off with is a direct application of the hydrogen bonds in the first 3 properties of water, which are all interrelated to each other. The first one is cohesion. The next one is adhesion. And then we have surface tension. So cohesion is the attraction of water molecules for each other. Adhesion is the attraction of water molecules for a hard surface. And surface tension is the force required to break the cohesive surface of water. Now let's take a look at it. You guys like, that went fast, too fast. Okay, let's take a look at it, right? So first of all, what we want to do is we want to take a look at and kind of break it down a little bit. First of all, so we have surface tension of water, which is driven by the cohesion of water. And so this is kind of what it looks like. So here we have a little water strider, right? Skittering across the top of the water. The question is, how does it keep from sinking? And the answer is quite simple. In order to overcome the surface tension of water, you have to have a downward force greater than the cohesion of water itself. Now let's take a look at what the water looks like underneath this water strider's feet. So basically you have negative oxygens and positive hydrogens. When water molecules are in and amongst themselves, these positive hydrogens will form hydrogen bonds with other water molecules like so. And they'll keep forming hydrogen bonds in this kind of like fishnet-like structure that just kind of keeps on going. No oxygens, oxygens to hydrogens, always. So the little dashed lines, these guys right here, this is a hydrogen bond. It's that electrostatic attraction. So here's what it looks like. So you got that negative-ish oxygen on water, just slightly negative. Seeing that slightly positive tail on water that's adjacent to it. And this positive and negative forms an electrostatic attraction to each other. So you can see how you start to form this little kind of structure, this sort of fishnet-like structure of water, all interlinked to each other. And those cohesive forces are strong, not individually, but corporately they're strong. Okay, so it's easy to break one or two, but a lot of them together becomes difficult to break. And that's an important principle because a good example of this would be like a gecko foot. Right? Anybody have geckos? You've seen a gecko foot, right? It's kind of got the little slots, right? Kind of like a little slotted foot kind of a thing. And you see the little dude kind of walking up the side of the glass and you look at it and you're like, how are you able to do that, right? Because the foot is slotted, not like suction cups, like an octopus. So it's like you can't do that one. So it's how do you stay up there, right? How do you not fall off the glass? Well, the thing is, what's holding them to the glass is hydrogen bonds. Now, any one hydrogen bond is not going to be strong enough to hold the gecko's weight, but there's millions of hydrogen bonds on each one of those little slotted folds on his foot that in accumulation creates more than enough force to hold his body weight on the glass. Not only that, but in concert, like in a cumulative sense, they have a lot of robustness, but they're still weak. Now, the reason why you have that is because the gecko wants to be able to pull his foot off of the glass too, doesn't he? So he wants a reversible reaction. When I put it there, I want you to stick. When I take you off, I want you to come off easily because I don't want to have to fight with you to get my foot off the glass. The fact that the hydrogen bonds are still weak allows him to reverse that very easily and replace it. So it's like a perfect, notice the pattern, reversibility. That is a key in biology. Everything you do, undo it, and then redo it, and then undo it, and redo it, and then undo it. That's the key. That's the mantra of biology. You don't just do stuff. You do stuff and you undo it, and you redo it, and you undo it, just like a light switch. Okay. This is the same example. You want to connect it and keep it. So you want some structure there. So you want to be able to, but then you want the flexibility to pull that off, to reverse it. And that's what hydrogen bonds do for you. If it was a suction cup, not going to be the same situation. Will he stick to the glass? Yes. But how easy is it going to get off of that thing? Not so much, right? Ask a starfish or a sea star, right? I mean, they're stuck to the side of the glass. I mean, they're like, you got to get the crowbar in there and peel them off, right? Because they're stuck there. Now, the gecko doesn't want that, right? Because technically speaking, the gecko has to run for his life, doesn't he? Yeah. Exactly, right? Because you are at the top of somebody's food chain, right? I mean, you're like top of their list, their menu. It's like, ooh, gecko. That sounds good
You
today.
actually see the mechanics of the gecko foot. He actually like pulls the very tips of the bird.
Like he kind of peels himself off. Yeah. And yeah, the nice thing is because what you're doing is like if you were to try to take his whole foot off, it would probably be a little bit more of a fight because you're trying to do all those hydrogen bonds all at once. So what you're doing is you're saying like, you know what, I'm just going to pick you guys off first, and then you guys, and you guys, and you guys. And he's using actually to his advantage this same principle of the cumulative strength or the diminishment of strength as you slim it down a little bit to his advantage. So really, the gecko is quite clever in using the nature of the hydrogen bond to a masterful effect. So how humbling is that? The gecko had this one figured out a long time ago. Well, we didn't even know about hydrogen bonds until 100 years ago. So who's smarter, humans or geckos? Geckos 1, I'm going to give them credit for it. Humans 0. Okay. Oh, it gets worse. Trust me. So that's the cohesion, right? So that's basically what holds water together. Like when water pours out of a faucet in a column, why it doesn't fly apart? It's because of the cohesion of the water molecule. Because what's happening is you're pouring out this chain, this interlinked chain of water molecules that are all zippered together by these hydrogen bonds, and they're pouring out in a column. And that's what keeps them in a column. Now, the water that the water strider is on is interconnected with these cohesive forces, these cohesive hydrogen bonds. So, and they're very strong. Water likes itself. So cohesion is a very strong property of water. What that does then is that basically means that it's going to take a little extra effort to break that relationship, which is the reason why we have this whole surface tension thing, where insects, for instance, the water strider can skitter along the surface of the water because it doesn't have enough downward force, not enough mass, to break those cohesive connections. Other liquids, by the way, will break just like that. They have no surface tension at all, right? Or if you really want to drown the water strider, you can add something to the water that will break up the cohesion of water, and then that'll change the surface tension and the insect will sink, right? That's if you want to kill the insect, right? We'll let them go. Now, what does this do for us? This is kind of cool because you can skitter along the surface of water and it's just kind of like a party trick. No, what's the biological application? Well, immediately what this does is it creates an entire habitat on the water. So you have an entire ecosystem below the water, an entire ecosystem above the water, and an ecosystem in its own right at the surface of the water. Look at a nice quiet pond like this or something like that, very still, not running water, because that chops up the tension a little bit, it kind of changes the surface tension. But look at a nice quiet pond and just watch what's happening at the surface. There's a lot going on there. There's all sorts of stuff happening. That's an entire little, that wouldn't exist without the surface tension of water. Good.
Could you swim in oil?
What?
Could you swim in oil because it doesn't have as much tension as water?
It's different. So you would sink in oil. So it's a totally different situation. And we would, so like oil would change that surface tension. So the water strider himself is adapted for water surface tension. So if you add even oil to it, you're screwed. Or if you increased his mass, like us, for instance, we don't live at the surface of water because we have too much mass. We easily break the surface tension of water because we have a lot of downward force because of our massiveness. This guy, not so much. Makes sense. Okay. Any other questions on cohesion before we get to adhesion? What? Oh, the walking on water thing? I don't know how that works. That's even in theological circles, that's nobody knows, right? There's like a series of like theological ideas that happen. That's just like, you know what, that's just like a miracle thing. Nobody knows. That doesn't make any sense naturally. Don't know how that happened. That's hardcore theology. That doesn't even get anywhere close to natural phenomena. It's just so out of the ordinary, which is why people like theology, because it kind of is just like, you know, rewrites their reality. But that's kind of, yeah, no. So a wider strider, I don't know. So yeah, but that'd be like one of those, like, you know, people say it's like, if, you know, if I see God, I want to ask him this, and this, and this would be a good one, right? So now how did that actually work out, right? You know, it's like, how did that work? Because that technically shouldn't happen. Yeah, what? Yeah, he's just, hey, yeah, I don't know. But yeah, that's I think they actually have an organism that's like the Jesus lizard, I think it's where it kind of like, yeah, it kind of runs on water a little bit. That's there, so there is kind of like an allusion to that same what you're referring to in actual biology. Now he's not technically walking on water, he's actually using his momentum to eliminate his downward force. That's what he's doing. So but basic idea. So okay, adhesion, right? What about this one? Well, cohesion, we know it's the attraction of water for itself. Now, what about adhesion? Well, adhesion we can actually illustrate quite nicely with a capillary tube. Does anybody actually know what a capillary tube is? 1, 2. Okay, that's better than most semesters. So generally speaking, you don't run into capillary tubes a lot. They're really, really small diameter glass, usually tubes. And usually you'll run into them in medical care. Oftentimes when you're trying to get a blood sample or some sort of a fluid sample, and you don't have, you don't have a syringe to work with, and you don't have an artery to go after, but you need, just a little bit of a sample, and you don't have access to it. And so what happens is you just basically stick that little capillary tube on the blood. You don't have to poke anybody with it, just stick it in the blood and it'll automatically suck up into the tube, right? Like magic. By the way, if you're keeping track, there's nothing magical about it. It's just a little glass tube. If you had a straw, that's a capillary tube. It's just a bigger diameter. By the way, the same set of physics also works. It's just that the movement of the fluid is so small that you don't even recognize it. But here's how the capillary system works. And we want to keep an eye on this. It's a dance between adhesion and cohesion. And I want to give you a couple of examples of this. One with the capillary tube, because that's going to cross over to our biological application. And one in sort of more lay terms, because that's going to cross over to our survival during winter. Like as snow shovelers and ice choppers to get out of our driveways and things like that. So just not like an organism. It's like, we're going to survive. No, it's like just getting through Denver during the winter. So the first thing is, when you take a look at adhesion or capillary, I'm going to blow this up. Generally speaking, you have two different forces as the water enters into the tube itself, right? The water column that goes into the tube is held together with cohesion forces, right? So all the water column is this little fishnet of like water molecules that are all interconnected with each other. I'm just going to try to, I'm not going to draw them out. I'm just going to sort of draw the little fishnet network, hopefully. Right, all these little water molecules that are connected to each other by cohesion, but then you add in adhesion. So what happens is these water molecules up here are going to feel and stick to the hard surface of the glass. When they do that, they're going to basically sort of smear themselves against the glass by adhesion. And when they do that, they don't let go of their associations with their water compadres. When they do that, they're pulling on the water column as they get smeared against the glass. That creates a gentle tug that will gently pull who you're connected to up, and then who you're connected to up, and then who you're connected to up, and then basically me pulling on you will pull the entire chain. So ultimately what you have is an upward direction of the water moving. So as I basically, if I'm kind of connected to you guys and I get smeared against the glass, I'm pulling on you guys and you're pulling toward me. So I'm pulling up the column. And then you're pulling on the folks that you're connected to in the water column below you as it's going up. Now, not only am I pulling you up because I'm getting smeared up here, but I'm kind of like pulling you up like this. And then eventually you're going to feel the glass and you're going to get smeared, which means you're going to pull the folks that you're attached to even further up. And as we all start to progressively get smeared against the glass, we're going to slowly pull each other up like a big interconnected column. And ultimately, if you take a look at that on a macro scale, that looks like water coming up the whole glass tube. That's capillary action. It's an interplay between adhesion and cohesion. Okay. Yeah, I mean, gravity is a thing, right? But gravity is constant. So when you actually have adhesion, it actually represents an excess of force. That's the reason why you have to have a smaller diameter so that you have more surface to stick those molecules to. And not only that, but a smaller column to pull up. So that's the reason why the liquid goes up higher in a small capillary tube like this guy right here. And in a larger capillary tube, it doesn't go up as high. Because even though I'm attached to you guys and I get smeared and you feel me pulling on you, pulling you up, if we have a big diameter, then you guys in the middle may never feel that effect because you're not all that close to the glass edge. So it's going to be, we're not going to go as high up because we're not pulling at each other. But if we're narrow diameter and it's just us three right here, if I get smeared, then you guys feel the full force of that smear and you guys get smeared against the glass. And so everybody feels it. That's what happens when it's a narrow diameter. Mm-hmm. Yep. Everything gets lifted up, right? So that's an example of adhesion and cohesion. Now let's take a look at our winter survival. Here's what I want to do. I want to take a windshield. I want to take a windshield and I'm going to treat it. On one, I'm going to treat it with Rain-X. What is that? Yeah, it's a product, it's a brand name, right? So basically what Rain-X is the coating that you can put on your windshield that basically wicks away water, right? And then of course the other one is not going to have any Rain-X on it. It's just going to be your straight windshield. Now let's take a look at rain. Okay, there's a couple things to learn. First of all, why is a raindrop shaped like a drop?
That's the most aerodynamic way for it to come down.
Nope. Yes, that's a good guess. But now what about gravity and cohesion?
Let's say gravity, it's pulling the most mass downwards, and cohesion, it's even though it's pulling the most, it's still trying to stay together as best it can.
Yes, and let's kind of compare it to a non-gravitational. Has anybody ever seen an astronaut playing around with water in space?
Yeah.
Right?
Blobs.
Yeah, it looks, and it's a perfect sphere, isn't it? Why? Because of the cohesion of water basically holds it in a perfect sphere. The only reason why our water drops are elongated is because we have a gravitational field pulling on that perfect sphere, causing it to elongate into a droplet. So you can see the cohesion is still there, right? Because it's still together, but you can see the gravitational effect and the distortion of what would otherwise be a perfect sphere. Now, the reason why I say that is because that's cohesion. Now what's going to happen as soon as the untreated raindrop hits the windshield? I like that little performance art. So, right, right. So what does that mean? It hits the windshield and then what? So it adheres and then it spreads out, doesn't it? Because that's the reason why you get that even coating of water on your windshield, is because the raindrop, basically as soon as it touched the windshield, feels adhesion greater than cohesion. How do you know that? Because everything's getting smeared across your windshield. That's why you need windshield wipers, right? So here, adhesion is greater than cohesion as soon as it hits that windshield. But what about Rain-X? What does it look like when a drop of water hits the Rain-X windshield? If you've actually looked at it closely, it's hard to follow because it moves quickly, but
I guess it really stick and it runs off.
It's hydrophobic.
So yeah, Rain-X I think is actually hydrophobic, but good. Hussein, you had a question? So it looks like, if you look at it, a perfect little bead, right? Smaller beads, but it's always a bead. It looks like almost liquid mercury, right? It just basically sort of beads up and then it just kind of rolls off of your windshield. It's awesome, actually. It works wonderful. So what is that? In this case, your cohesion is greater than your adhesion. Why? Because you're hiding the adhesive surface with Rain-X. So the water never feels the adhesive force and it just rolls right off. So when your windshield wipers are streaking, consider buying some Rain-X instead of replacing your windshield wipers. Because, well, Rain-X could be cheaper. Rain-X? Well, Rain-X is a brand name. You get it in most like auto parts stores, but there's other non-Rain-X brands that basically do the same thing. Yeah. Yeah, they're water repelling. So
My windshield wipers just broke, so I think.
yeah.
maybe it's best
Well,
to-
hey, it works. It works because I used it in Kansas when they get torrential downpours, and it works wonderfully. So,
Do you? Hold on, yeah.
but I was actually thinking about it because I don't want to replace my windshield wipers. I hate it. It just drives me crazy. They're like, "Oh, your windshield wipers are streaking." Yeah, so I'm not going to change them. Right. I'm just going to add some Rain-X to my fluid and just spray my windshield with Rain-X. We'll all be good. So, yeah. Yeah, my windshield wiper fluid is crazy. It's like a concoction of Rain-X and de-icer and anything but water, right? There's no water in there at all, just the concoction of chemicals. But who cares? I got a 15-year-old Ford, so yeah, right. So, yeah, anyway, that's that. So here's the pretty image of water, right? So you can see you've got your hydrogen atom forming your hydrogen bond with oxygen. That's your water. By the way, if you have an organic molecule that's also polar, you can do the same thing, right? So if you have that positive hydrogen there, you can basically form that hydrogen bond with the polar molecule as well. That's another trait, by the way, we'll get to shortly. Okay, but first of all, before we get to specific heat, I want to follow it because I promised you a biological application. I haven't given to you yet, but I'm going to now. So here's the thing. Where does this come into play? This is all great. We saw Ryder Strider. That's kind of cool with surface tension. Okay, got that one. But outside of going out and making a run on Rain-X, what actually does this do for us, really? The whole adhesion thing. Well, number one is two. For you personally, as a bio student, when you're measuring volumes, if you measure volumes, especially in like glass, you notice a meniscus. Why does it curve upward? Because of adhesion. So the reason, notice how I drew this as a U. That's the way it looks when you're looking at like a glass graduated cylinder. So when you read a meniscus, you read it at the bottom of the meniscus, not at the top. But the reason why it curls upward is because of the adhesion. It's the water sticking and feeling the glass. It pulls that up. Okay. So that's one. But the other one is this. Yeah. It's either that or an inverted feather, right? Yeah, right. It's a tree going Bob Ross style. Happy little tree, minus the throw. Huh? Yeah, right. So the thing is, now this is a tree, right? But this isn't the scrawny little thing in your backyard. This isn't the scrawny little things that we see here in the Rockies. You know what this guy is? Yeah. This is one of those ones that you drive a car through, right? Because they're like 200 feet up. So here's the question. You have to get water up there, don't you? How do you do it? Gravity's pulling down on you. how do you get the water up there, right? You've got your root system here. Exactly. You basically have a capillary inside the trunk of a tree.
Oh.
The vascular tissue acts like a capillary. Now, notice what we said with the capillary, right? The smaller your diameter, the higher it goes. The tracheids, which are the little vessels in the vascular tissue of a tree, are microscopic. So they are like tiny diameter, like to the nth degree. And there's a lot of them. So you're going to get water coming from the roots and easily going up that super, super narrow diameter by adhesion all the way up the trunk of the tree to the crown of the tree where it evaporates. And when it evaporates, guess what it does? It creates physiology wise, right? For plant physiology, it actually creates a tension itself. So it's like if we're interconnected as water and like I'm at the crown of the tree and the tree gets ready to evaporate me, then my loss kind of tugs on you guys and you feel the deficiency of that water, which further motivates the replacement of me at the crown. So you're always trying to fill that, like the void that I left. The water
that
column
keeps on
feels
filling up.
all the way through the column and says, we got to fill that void because Mark just left. And you fill that by pulling the water column up. So now you guys are at the crown and then you guys get evaporated off the tree and then the column continues to move. So you keep this kind of cycle of evapotranspiration as your water molecules leave the crown. And of course, other areas of the leaf as well. Okay. So that entire plant wide creates a massive like upward pull along with the capillary action creating an upward pull. So getting up to 200 feet, no problem.
Video where someone was trying to pull water through a root, but then they're taking at the point where it started using about boil. That happened.
Well, I'm not sure how that has anything to do with boiling, unless what they had was some sort of a pressure situation going on there. If they were using pressure, you can boil water at room temperature. So boiling actually doesn't have anything to do with temperature because you can boil at room temperature if you create a vacuum, right? So if you basically put a beaker of water in a bell jar and you evacuate it, you can get the water to boil at room temperature. A bell jar, yeah, not a ball jar, not like a canning jar. Yeah, it's like, yeah, but a bell jar that has a seal that's designed to be evacuated. If you evacuate that, you can actually make water boil at room temperature. And actually, we see that effect atmospherically, right? Because when you guys boil water, and I could have you guys do this, I can grab a thermometer and you can test this because we're going to be using boiled water to develop our Benedict's tests in lab. But when you get that thing to a roiling boil, put a thermometer in there. Tell me what you read. In Denver, you don't get to 100. In Denver, boiling is the best I've seen is about 92. Usually it's around 90 or so.
So the higher up you go.
Because of the pressure difference, you have a high, because of the lessening of the pressure, it creates a depression in the boiling point. So that's important, right? Because for those of you guys who like to get up into the mountains, up by the divide, 12,000, 13,000 feet or whatever, and you're up there camping and you're pulling from the stream and you're boiling your water for your safety measure, remember, you're not killing what you think because it's not as high. You're probably boiling that water in maybe at the 80s. And so you just better hope that all your organisms are dying at that temperature, because if they have any stick-to-itiveness, then you may not be getting everything, which is the reason why they always say, don't just do one, do two. Boil, filter, filter, boil, boil, treat, do something, right? But do two of them, not just one. That's why. Is because of that boiling point depression. But try it. We can pull out a thermometer on Friday and we could take a look at it and see what our boiling water gets to.
What was that disease called when you drink, you mentioned like
Giardia.
Yeah, when you like drink.
Yeah, Giardia is a protist, and it hangs out in seedy places, usually stagnant ponds and things like that. That's the reason why, you know, they always say, you know, if you drink from, make sure you drink from moving water. That has typically, like when I am hiking, like when I scope from water, I spend a lot of time actually when I get ready to set up camp, I scouting out my water sources and characterizing my water sources. And so I will actually spend time like going upstream and then going downstream, and I'll like look all the way around my campsite to try to figure out like what is coming from upstream. Is there a stagnant pond up there that's not a good idea? You want to get above that stagnant pond, where preferably you want like fresh snow melt coming off. That's usually the best. But oftentimes I'll even actually trace where that original snow melt is coming from. So I'll be like, okay, where's this coming from? So is there like an ice sheet here that's melting into this moving water, and does it have a lot of algae growing in it and stuff like that, or not? So I kind of look at it, I check it out. The cleaner and the whiter the snow or the ice, the better. And the more faster moving it is, the better. And I try to get as far upstream as possible. So sometimes just to get water, drinking water, I'll actually take my camp and I'll actually trek like a mile upstream just to make sure that you get upstream of where typical camping zones are, so that you don't get, you know, inclusions and things like that on water. But even then, you know, it's always a gamble. So that's, yep, always filter, boil, and filter. Do two things at a time. Okay. So, and that's why I spend a lot of time water treating. It's like, people, what do you do when you're hiking? Oh, water treat, right? And get my water ready, because I like to drink coffee. That's one of my favorite things, is to have a nice hot cup of coffee, like early in the morning up in the mountains. It's like nothing better than that. And, but you know, that means basically that the previous day, I'm pretty much doing nothing but just treating water. I mean, a lot of it, you know, I'm just filtering and boiling and cooling, and it's like I'm a little water plant up there. Yeah, so they're like, that's all you do? I don't want to, trust me, you don't want Giardia. You have to go to the hospital and get IV if you get Giardia. It doesn't go away. Yeah.
A bad time.
Yep. So, good.
Do trees evolve for like higher altitude, like the whole like vision works through them, so they get, you know what I mean, like what are they, the capillary? Do they have like different capillaries higher up in the
They do, actually, because pine trees are more robust in boreal environments, and that's typically what you see dominated up by tree line. And typically, when you take a look at flowering plants and non-flowering plants, of which pine trees are non-flowering plants, the vascular tissue in flowering plants is a little bit different. And it's a little bit more like our vasculature. Honestly, it looks like it's still like little tubes, but they're not quite as severe as what's in pine trees. So if you take a look at pine trees, they have a more kind of a primitive style vessel, which is much tinier, much more restrictive. And that's probably part of the adaptation to that level of environment, to make sure that you get enough adhesion to get up to the crown. And so there's a lot of innovations. That's the reason why you don't see a lot of flowering plants or trees at elevation. You see more of the gymnosperms up there, not angiosperms. Okay. And that's part of that. That's the whole development of angiosperms and gymnosperms is a fascinating story. It's all right. So what I want to do, so we have 5 minutes, and I'm going to take it. But what I want to do is, I don't want to dig deep here. I just want to sort of open this up, kind of like I did before, just kind of lay out some of the definitional components of this, and do the deep dive next time. Okay. So what I want to do is I want to take a look at a related set of properties of water that are nevertheless really, really critical. And the first one is basically what's called specific heat. So there's what's called a high specific heat. We'll talk a little bit about that. I want to unpack that one a little bit. Along with that one is another type of a thermal property of water along with specific heat. And that is it's got a high heat of vaporization. And then the next one, which is not a thermal one, but it is kind of related a little bit to it because it's one of the properties of the states of matter, like liquid, gas, and solid. And it does something very unique. The solid is less dense than the liquid. Now, cohesion, adhesion, surface tension, those were cool, right? Because they create a lot of biology for us. But these ones are critical, right? So I would call these sort of related in the sense that these have to be in place the way that they are if we want to have any chance at life. I mean, these are that critical, right? So these properties literally are life and death properties. They are the difference between living things on the planet and no living things on the planet, which is one of the reasons why we're looking for liquid water. We'll talk a little bit about that and why not looking for ice and things like that on other planets. But these are kind of interrelated. And what I want to do is I want to sort of take a little bit of a look at these guys and kind of sketch these guys out. But I want to build these in because they are energetic principles. And remember, I said that because we're doing the energetics sort of on our own, I cherry pick the ideas of energetics and I interlace them through the chapter material as we get there. This is an example of that, where there's ideas, general principles of energetics that we meet in chapter 6, 7, and 8 that I picked specifically out to interweave it into our discussion of something else where the energy kind of weaves into the tapestry of it all. And I want to make sure that we have plenty of time to sort of develop that energetic story, right? Okay, so we're going to talk a little bit about that next time. So I'll stop there and then I will let you guys think about that. Make sure you guys are ready for Friday. We're doing labs 3 and 4, mostly 4, by the way. None of the sections that we've done labs for so far have ever even gotten close to doing 3. So if you have time to read 3, great, but start with 4, focus on 4, and then we'll be ready for the quiz on Friday.